नमस्कार बच्चों, मेरा नाम धन्या और हम लोग सीख रहे हैं ग्रेड 11 केमिस्ट्री का 4th लेसन केमिकल बॉन्डिंग, जिसमें आज हम लोग सीखेंगे डाइपोल मोमेंट. We will be learning about dipole moment. We will be learning about polar and non-polar compounds, how to identify them, and also how dipole moment is used to find the percentage of ionic character. Okay, and this particular topic is very important for competitive exam. Okay, so suppose I have a compound hydrogen and fluorine, hydrogen fluoride. Okay, this is a bond, and you know that fluorine is highly electronegative, so it will pull the electron pair towards each other, as a result of which chlorine will develop a slight negative charge, hydrogen will develop a slight positive charge. So that means these are called as polar ends. Chlorine having slight negative charge, hydrogen having slight positive charge. So these are called as poles, polarity. Okay, so why this polarity is developed? Because of difference in electronegativity between the atoms. Okay, and we can say that this particular compound or this particular molecule is polar. Okay. Sometimes when there is no electronegativity difference, the molecule is said to be non-polar. For now, we will assume that. But if I take an example, BF3, fluorine, fluorine. Okay, we know fluorine is highly electronegative, right? So that means if there is a lot of electronegativity difference, this bond should be polar. So that means this particular compound should be polar, but experimentally, this molecule is non-polar. We will learn about this. So that means having a difference in having polar ends or having positive or negative charge is not the only criteria to determine the polarity. So to determine the polarity, we need to learn about dipole moment. Dipole moment helps to understand which compound is polar and which compound is non-polar. Okay, so dipole moment helps to determine whether a covalent compound, we will be talking about covalent compound, whether it is polar or non-polar. Okay, so dipole moment. So coming to dipole moment. Dipole moment is represented by P or mu. Okay, most of the books use this mu. And mu is a dipole moment is a vector quantity. Dipole moment is a vector quantity. I'm sure you must be knowing what's a vector quantity. Those that have both magnitude and direction. Okay. And the dipole moment mu is given by Q times D. This is the formula for dipole moment, where Q is the charge on any one of the atom. Okay, and D is their internuclear distance. Okay, so if I have hydrogen chloride, charge for finding out mu, we will take the charge of any one of the atom and the internuclear distance between the atoms. Okay. Then, how to express the direction from which atom to which atom? Usually, suppose we take the same example, hydrogen chloride. Okay. Chlorine is more electronegative, so it develops a negative charge. Hydrogen gets a positive charge. Always the direction is from positive to negative like this, or from the less electronegative atom to more electronegative atom. So this is the direction. From the less to more, or we can also say from positive to negative. Okay. This is first way of expressing the direction. In case if lone pair, LP stands for lone pair. We have been using this in so many videos. Lone pair is there. Suppose I have an atom A. I have an atom A, and this is the lone pair. Then the direction is from the atom to the lone pair, like this. So it is from atom to lone pair, where LP stands for a lone pair. This is how we express the direction. So dipole moment, we will be using mu for this video. It's a vector quantity. That means it has both magnitude and direction. It is given by the formula Q times D, where Q is the charge of any one of the atom and D is the internuclear distance between the nucleus of the two atoms. Okay, mostly it will be given in the question if they ask you to find out. Okay, then direction, how to express? It is expressed from less electronegative atom to more electronegative atom, or from plus to minus. Or in case if there is a lone pair, then it is expressed from atom to the lone pair, as it is shown in case B. Okay, now in case of molecules, okay, or in case of compounds, okay, we usually check the net dipole moment. If the net dipole moment is 0, it is the molecule is, or the compound is non-polar. If it is not equal to 0, then it is polar. Okay. Usually we check the net dipole moment. Mu net means net dipole moment. For example, if we talk about carbon dioxide, okay, so this is carbon dioxide. It has a linear structure, okay, and you know that oxygen is more electronegative, so direction from positive to negative. Then this is positive, this is negative. The direction is from positive to negative. Okay. On both sides, we have dipole moment. But if both of them, if the dipole moments are in the opposite direction, they cancel each other. They cancel here because they are in the opposite direction. The net result is that they cancel. So mu net is equal to 0. That means carbon dioxide is non-polar. Even though there is a difference in electronegativity, still it is non-polar. Why? Because this dipole moment is, the individual dipole moments are cancelling each other. Okay? So, if there are individual dipole moments like this, mu, and if they are in the opposite direction, they cancel each other, and the net dipole moment is 0, and the molecule is non-polar, or the compound is non-polar. So you can see here, there is individual dipole moment mu and mu, okay? So it is there, but still it is because they are in the opposite direction, they cancel each other, okay? So even though there are compounds with electronegativity difference, just like carbon dioxide, they are still considered non-polar. Why? Because the dipole moment, they cancel each other. Okay, so these two cases you must remember, that when mu is equal to 0, the molecule is non-polar. If mu net is not equal to 0, then it is polar. So irrespective whether the electronegativity difference is there or not, mu can be 0, mu cannot be 0. That depends upon the dipole moment, whether they are cancelling each other or not. If they cancel each other, even with electronegativity difference like this, like carbon dioxide, even there is an electronegativity difference, we consider it as non-polar. Why? Because the individual dipole moment, they cancel each other. Okay, I hope it is clear till here. Now let's consider some type of molecules. Okay, so this should be in your mind. Okay, so diatomic molecule. First one is homoatomic. Homoatomic means that molecule is made up of same atom. For example, hydrogen, nitrogen, okay, oxygen. All these are homoatomic. That means both the atoms are same. For example, hydrogen and hydrogen, both the atoms are same. Chlorine, chlorine, both the atoms are same. Bromine, bromine, both atoms are same in the molecule. Okay, now here, straight away we can write for them the electronegativity difference. Because it's the same atom, there is no electronegativity difference, and the dipole moment is equal to 0. Straight away we can write, because both the atoms are the same. Because both the atoms are the same, we can directly write that the dipole moment is 0. So we consider them as non-polar. Why? Because both the atoms are the same. So the net dipole moment is 0. Okay, so it is non-polar. So this is easy, right? Then here we will come to a lot of cases. Heteroatomic. Okay. In heteroatomic, that means a molecule is made up of two different type of atoms. For example, HF. This is heteroatomic, or HCl. This is also heteroatomic. Two atoms, different atoms. Then I have HBr, heteroatomic, HIO, also heteroatomic. Okay, so here there is electronegativity difference. So they will attain positive and negative charges. Poles are formed. Here also there is difference in electronegativity. Poles are formed. Here also there is electronegativity difference. So poles are formed. Here also there is electronegativity difference. Poles are formed. Now, in this, there is polarity. So the net dipole moment is not zero. So all these molecules will be polar. Now the question comes, who will be more polar? Who will be more polar? Suppose 1, 2, 3, 4. Okay, I have numbered them. Who will be more polar? Okay. Now here, in HF, fluorine has a higher electronegativity, right? So, in this case, we consider the charge factor. We can consider the charge factor for fluorine, right? But in case of HI, we can consider the size of iodine is bigger, right? So we consider the distance between the atom will be bigger in case of HI. Okay, so considering if we have two factors coming into play, the charge factor and the distance factor both coming into play, usually we give importance to the charge factor. So here, because the dipole moment is directly proportional to Q and D, we consider the charge factor more. Okay, so if both our factors are coming into play, the charge factor is taken into consideration more. So in this case, what will be the order? Definitely, the charge factor for hydrogen fluoride is more. It will be greater than hydrogen fluoride. It will be greater than hydrogen bromide. It will be greater than hydrogen iodide. Okay, so we consider the charge factor when we have a situation like this where we have to consider both charge and distance both. Okay, I hope it is clear till here, right? Sorry, I hope it is clear till here. Okay, students, this was for heteroatomic. Okay, let's move on to some more examples. Polyatomic molecules. Okay, we will be talking about slightly bigger molecules. Okay, in polyatomic, the first one we will take is AB2. 3 atoms. Till now we were dealing with 2 atoms. Now we will start 3, 4, 5 like that. So AB2. So that means BeCl2, carbon dioxide, 3 atoms making a molecule, C2H2. Okay. Now, suppose I have beryllium chloride. Okay. Now, the electronegativity difference from beryllium is less electronegative, chlorine is more electronegative. So, arrow is from less to more, less to more. Okay. Now, are these arrows in opposite direction? Just like a moment ago we saw about carbon dioxide. If they are in the opposite direction, the net dipole moment is 0. That means it is non-polar. So even though there is an electronegativity difference, this molecule is non-polar because the dipole moment or the net dipole moment is 0. Similarly, we just saw a while ago about carbon dioxide. Carbon dioxide is C double bond O, C double bond O. And the net or the dipole moment, individual dipole moment is there. Carbon is less electronegative. So from less electronegative to more electronegative oxygen. Less electronegative carbon to more electronegative oxygen. So here also, if the dipole moment, there is individual dipole moments, but they are in the opposite direction. So if they are in the opposite direction, they cancel each other, resulting in mu net equal to 0. Dipole moment is 0. So this is non-polar. Okay. Similarly, if I have ethyne, C triple bond, C, H, H. All these structures you will be learning in grade 11. So don't worry as we move on. Okay. Usually, hydrogen is less electronegative. So compared to carbon, okay. So the arrow is from less electronegative to more electronegative. So it is like this. Okay. Now, here also, there carbon and carbon, between carbon and carbon, there will be no electronegativity difference because it's the same. Okay, so here also you can see mu net is equal to 0 and the molecule is non-polar. Okay, so here I will make a note over here. I think I should make a note over here. In all these examples, what you saw is if polyatomic means it can be 3, 4, 5 like this. We will be taking few more examples. But for now, if there are polyatomic molecule and if it is symmetric. Symmetric means it is surrounded by same type of atom like oxygen, oxygen here. Chlorine, chlorine, hydrogen, hydrogen. It is surrounded by same kind of atom. Okay. And surrounded by same kind of atom. Then mu net or dipole moment is equal to 0 and the molecule is non-polar. Provided, what should not be there? Provided there is no lone pair. We did not talk about the lone pair, but here, what is the condition? There should be no lone pair of electrons. Okay. So I hope students, this note is, you have noted down this note. So in case of a polyatomic molecule, polyatomic means those that have 3 atoms, 4 atoms, etc., which is symmetric. Symmetric means same from all the sides. For example, carbon dioxide, it is same from both the sides, right? So such molecules are called symmetric, okay? And which is surrounded by same kind of atom, okay? The net dipole moment is 0 and it is non-polar. And what is the condition? Provided that there is no lone pair present. If the lone pair is present, then the story will be different. We will be learning as we move on. Okay. Now, let's move on to the next type of polyatomic. That is the second type, AB3 type of atom. That means there are 4 atoms in total. For example, BF3, okay, BI3, BBr3. Okay, now over here, I have boron, fluorine, fluorine and fluorine. Okay. Now, this is symmetric. Yes. So this is symmetric and it is surrounded by same kind of atom. Symmetric means same from all the sides, all the directions. Yes. So it is surrounded by the same kind of atom, that is fluorine. So the net dipole moment is 0. But let's check out. Let's check the direction of the dipole. So fluorine is more electronegative. So this is the dipole moment. Then this fluorine is more electronegative, from less electronegative boron to more electronegative fluorine. So this is the direction of the dipole. Okay. And all the three of them, all the three dipoles, suppose consider the individual dipoles as mu. Mu, mu, mu. So there is individual dipole, but these individual dipoles, they are in opposite directions. You can see mu, mu, mu. They cancel each other. So mu net is equal to 0. So you can see this is symmetric molecule and have same kind of atom, surrounding atom, which is fluorine, surrounding atom. So the net dipole moment is 0. They cancel out each other. Okay. So same way for Bi3 and BBr3. Okay. Now, considering another example where I have sulfur trioxide and sulfur dioxide. So compare the dipole moment of SO3 and SO2. Okay. So sulfur, we learned making the structure of sulfur trioxide when we were doing the Lewis dot structure. So there are 3 triple bonds. Sulfur shows a covalency of 6 here. We learned this. Okay. Right. This is also a symmetrical molecule, same from all the sides, and the surrounding atom is same. Yes. And there is no lone pair. That's also a condition. So here, what is the direction of the dipole? Let's check. From less electronegative to more electronegative oxygen. From less electronegative to more electronegative oxygen. From less electronegative to more electronegative oxygen. So the 3 dipole moments cancel each other, and there is individual dipole, but the 3 of them cancel each other. So net dipole moment is 0. It is symmetrical. Symmetry is there. No lone pair. So it is non-polar. And the net dipole moment is 0. That is why it is non-polar. Okay, see, it is the 3 dipoles cancel each other. It is in all of them, they are in opposite direction. Similarly, if we consider sulfur dioxide structure also we studied when we were doing the lesson on Lewis structure. And there is a lone pair of electrons. Okay, so let's draw the dipole. The dipole is from less electronegative sulfur to more electronegative oxygen. Let's make it as mu. Less electronegative sulfur to more electronegative oxygen. Both these mu are the same, but here there is an additional situation of lone pair. So the dipole is from the atom to the lone pair. So this dipole is not the same as the other 2 dipole. So I make it mu dash. So this mu dash is not same as mu. So although they are in 3 different directions, like the sulfur trioxide, this is mu, this is mu, this is mu dash. They are in different directions, but mu dash is not same as mu. So that is why there is a net dipole moment. Net dipole moment is not equal to 0. So that means this molecule is polar. I hope you are clear. So here, although the 3 dipoles are in opposite direction, but the dipoles, because of sulfur and oxygen, is different from sulfur and lone pair. Okay, so even though they are in different directions, the dipoles are different. So this gives a net dipole moment. If there is a net dipole moment, the molecule is polar. Okay, I hope this is clear. This is very important. Okay, so moving on further, let's take AB4 geometry tetrahedral. CCl4, which is very important. Usually they ask questions. CH4, SiF4. Okay, now if we say carbon bonded to 4 different chlorine, it's a symmetrical molecule. It is symmetrical. No lone pair. And surrounded by the same type of atom. So that means it is non-polar. We can directly say, even same thing for methane also. Okay, so methane, hydrogen, 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 hydrogen. Okay, so here also it is symmetrical. There is no lone pair and symmetrical, same from all the directions. And also, what is the third condition? There is no lone pair. It is symmetrical and surrounded by same atoms. So directly, it is non-polar. Same is the case of SiF4, that is also non-polar. Same conditions apply. No lone pair, symmetrical, and surrounded by the same kind of atom. But let's go to that exception where if I take CH3F, CH2, Cl2, CHCl3, CH2, F2. This is also of the kind AB4. The central atom is surrounded by 4 atoms, 3 plus 1, 4. Central atom carbon is connected to 2 hydrogens and 2 chlorine, total 4. So they are all of the AB4 category. So do you think their dipole moment will be 0? No, because they don't have symmetry, no symmetry. They don't look same from all the sides, and also they are not surrounded by same kind of atom, not surrounded by same kind of atom. Like the first one, with carbon there are 3 hydrogen and 1 fluorine. With second one, B, there is carbon connected to 2 hydrogen and 2 chlorine, not the same kind of atom, right? So all of them, they are polar. Okay, so you have to check this also. AB4, this is also the AB4 type, but they are connected to, the central atom is connected to different kinds of atom, and there's no symmetry. Okay. Now moving on further to AB5 kind. Okay. So we have PCl5 is an example, PI5. Okay. So we learned the structure. Okay. Remember PCl5, trigonal bipyramidal, three of them in the same plane. And Cl, Cl, Cl. So this is, make some space for phosphorus. Three of them in the same plane, one above and one below. Okay, axial and equatorial bond. We learned this in the previous lesson on valence shell electron pair repulsion theory. Trigonal bipyramidal. The three of them that I have drawn in red, they are in the same plane, right? And they are in the same plane. So mu, mu, mu. They cancel each other, right? This one, they cancel each other. And I still have one above and one below. The equatorial one above and one below. They also cancel each other. They also cancel each other. So this mu cancels this mu. So the net dipole moment is equal to 0. Okay, so these molecules are non-polar. So in simple words, if I say this is mu, mu, and mu, these three of them cancel each other. And this is mu dash, they also cancel each other. Okay, in fact, it is mu only because the surrounding atom is the same. So here mu of the equatorial bonds, they also cancel each other, resulting in mu net equal to 0. And hence, what kind of molecule it is? It is non-polar. So these molecules are also non-polar. Okay. Coming to AB6. SF6. Okay. Now here, the structure is 1, 2, 3, 4, 5, 6. All connected to fluorine. This is a symmetrical molecule, you can see. And this is symmetrical. Surrounding atoms are same. So mu, there's no lone pair. Also, no lone pair. So mu net is equal to 0. So it is non-polar. Okay, so this is non-polar. I hope it is clear. So this condition is very important. Okay, so surrounding atoms being symmetrical and absence of lone pair will make the molecule non-polar because the net dipole moment is equal to 0. Okay, I hope it is clear now. Now, coming to a question, compare the dipole moment of water, ammonia, and ether, CH3, O, CH3. You will be learning about these structures, okay? Ether, all the organic compounds, okay? Now, water. Water, you know the structure. Oxygen is connected to, bonded to two hydrogens, and there are two lone pair of electrons, okay? Now here, the dipole is from less electronegative hydrogen to more electronegative oxygen, less electronegative hydrogen to more electronegative oxygen. And also, apart from this, there is also dipoles from oxygen to the lone pair, because there is lone pair, oxygen to lone pair. Okay, so I'll draw it a little bit bigger. Okay. So I have oxygen, hydrogen, hydrogen. There is lone pair. There is lone pair. Okay. Now, there is dipole from the less electronegative hydrogen to more electronegative oxygen. Less electronegative hydrogen to more electronegative oxygen. Also, there is dipole from oxygen to atom to lone pair, from atom to lone pair. Okay. So here, the dipole moments are not cancelling each other. There is a net dipole moment. Okay, so here the lone pair is present. The dipoles are not cancelling each other, right? So the net dipole moment is equal to 0. Okay, so see here, in case of water, if you see the dipole moment not cancelling each other, right? In fact, there is a net dipole moment. So in water, they are not cancelling each other. In fact, they are adding up, if you see. Okay, so here the dipoles are getting added up. They are not cancelling each other, but they are getting added up. So just as a hint, whenever there is lone pair, that means probably it will be polar. Okay, so in water, because of the lone pair, the dipoles are not getting cancelled. Okay, in fact, they're getting added up, and the net dipole moment is not 0. So that means the molecule is polar. Okay. In case of ammonia, let's check for ammonia. Nitrogen. There are 3 hydrogens, and there is a lone pair of electrons. Dipole is from less electronegative hydrogen to more electronegative nitrogen in all the 3 cases. Okay. Now here, also, you can see that there is another dipole from atom to the lone pair. Here also, if you see, the dipoles are not cancelled. Not cancelled. Okay. They are in the same direction, and the net dipole moment is not equal to 0. So that means this molecule is also polar. Okay. So another example is the ether. So I have oxygen. This is CH3. This is CH3. Here also there's a lone pair of electron. In fact, 2 pairs are lone pair. and the dipole is from methane to more electronegative oxygen in both the cases. And also there's a dipole from oxygen to lone pair, from oxygen to lone pair. Same case like water. Okay, here also they are getting added up and the net dipole moment is not equal to 0. So this molecule is also polar. Okay, so all the three of them, the dipole moments are not getting cancelled. So that is why they're getting, in fact, added up, and that therefore they are all polar. Okay, now, in case of an example we just saw before, sulfur dioxide. There is a lone pair, and we drew the dipoles here, mu and mu. This is mu dash. Here, although we feel that the dipoles are getting cancelled, but they are all the three of them, they are in all the dipoles, they are in different directions, on opposite direction. We feel that they might get cancelled, but we saw before that mu dash is not same as mu and mu, because mu dash is because of what? Lone pair of electrons. So that is why this molecule is also polar, just to bring about the difference. Okay, so this is also polar. So all these four molecules are polar: water, ammonia, ether, because the dipoles are not getting cancelled. Okay, they have a net dipole moment. Okay, they are not going in opposite direction. If you see, the arrows are not in opposite direction. Okay, there is a net resultant dipole is there, so they are all polar. In case of sulfur dioxide, although the dipoles are in opposite direction, but the dipoles are different. You can see one dipole is because of the lone pair of electron, so it cannot cancel the other two. So even though we feel that they are in opposite direction, there is a net resultant dipole. It is not equal to 0 because mu dash is not same as mu. Okay. Okay, students. Moving on to an exception. Exception. For example, if I say XEF2. Okay. Now, let's find out the shape for Z value, half of number of electrons in the outermost shell of the central atom, that is xenon, is 8. It's a noble gas. Plus, there's no positive or negative charge, but there are two monovalent atoms. I hope you remember the formula. We did it in the previous video. And this is 5. Okay. So out of 5, 2 are used to form the bonds. 2 electron pair is used to form the bonds. So there are 2 bond pairs and 3 lone pair. Okay, so we just want to know the lone pair, how much it is present. Okay, so here xenon, it is trigonal bipyramidal. Okay, now here I have 3 of them in the same plane, 1, 2, and 3 in the same plane, and equatorial bonds. I will keep the fluorine over here, and the lone pairs I'll keep it here in the same plane. Okay, so this is the lone pair of electrons. This is the lone pair of electrons. Now, the fluorine, the dipole here for fluorine will cancel this dipole. Okay, so over here, I'm placing the 3 lone pairs. Okay, so the lone pair, the direction of the lone pair, the direction of dipole is from xenon to lone pair, xenon to lone pair, xenon to lone pair. All the three mu's cancel each other. So let's consider them as mu. Okay, this is mu, mu, and mu. All the three mu's cancel each other. Then, so this is mu, mu, and mu. Because the direction is in opposite direction from the atom to the lone pair. All of them, they are in opposite direction. They cancel each other. Now, coming to fluorine. Fluorine is more electronegative. Fluorine is more electronegative. So, mu dash, mu dash. The direction is from xenon to fluorine, xenon to fluorine. That is also in opposite direction. So, the net mu is 0. So this molecule is polar. So this is an exception to a case that even though there is lone pair of electrons, still the, this is 0. So it is non-polar, non-polar. So this is an exception to the case. Even though there is lone pair, the molecule is non-polar. Okay. Similarly, I have XeF4. Z value, half of number of electron in the outermost shell plus monovalent. There is no positive or negative charge. So this is 6. Out of 6, 4 is used to form the bonds. So 2 lone pairs and 4 bond pairs. So it is octahedral geometry. So xenon. So I'll keep the lone pairs here. And I'll use the fluorines at this position. Fluorine, 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 fluorine. Yes. So there are 2 lone pairs. The direction of dipole is from the atom to the lone pair, atom to the lone pair. So if I consider mu and mu, do they cancel each other? Yes, they cancel each other. Mu and mu cancel. Why? They are in the opposite direction. Now, coming to fluorine, which is more electronegative. So I have the direction, I'll use another color. Xenon to fluorine, xenon to fluorine, xenon to fluorine, xenon to fluorine. All are in opposite direction, mu dash, mu dash, mu dash, mu dash. So you can see that all are in opposite direction. So what is the result in mu? Mu net is equal to 0. So it is non-polar. So this is an exception. Even if there is a lone pair, we have non-polar molecule. So this is an exception. Okay. Now, I hope it is clear. Okay. So I'm checking the direction of the dipoles. Okay. Over here. These 2 cases, these are the 2 exceptions. Okay. Moving on to an organic molecule. I have carbon connected to carbon. This is hydrogen. This is chlorine. This is chlorine. And this is hydrogen. Same way over here. Carbon connected to carbon. Chlorine. This is hydrogen. This is chlorine. And this is hydrogen. Okay. This is A and this is B. Okay. Now in these 2 cases, can you see some difference over here? In A, chlorine, both the chlorine and both the hydrogen are in opposite direction. Okay. We call it as trans. You can see hydrogen and hydrogen, they are in opposite direction. Yes. But in the second case, you can see hydrogen and hydrogen in the same direction, chlorine and chlorine in the same direction. We call it as cis. You will learn this in grade 11. Okay, more details about this cis and trans. Okay, these 2 molecules have the same formula, but the structure is different. Okay, so here, let's check out the dipoles. Over here, from less electronegative hydrogen to carbon. Okay, over here, chlorine is more electronegative. Chlorine is more electronegative. Carbon is more electronegative. Okay, this mu and mu cancel each other. Yes, but mu dash, mu dash. So mu and mu cancel. So in trans, in case of hydrogen, the dipole is from hydrogen to carbon. This is mu dash. Hydrogen to carbon, that is mu dash. Now, if you see, mu and mu are cancelling. Mu and mu are cancelling each other. And same with the case of mu dash and mu dash. They also cancel each other, resulting in a net mu of 0. That means it is non-polar. Nothing is getting added up. They are cancelling up. Okay. Now, in case of cis, I draw the dipole from carbon to chlorine, from carbon to chlorine. This is mu, this is mu. And for hydrogen to carbon, hydrogen to carbon, this is mu dash and mu dash. Here you can see that the dipoles are not getting cancelled. So there is a net dipole. It is not equal to 0. So therefore it is polar. Okay. So usually the dipole moment, or you can say the dipole moment of cis is usually greater than trans. Usually. Okay, not always. We have exceptions also. So for now, in trans, they cancel each other. That's why there's a net dipole moment of 0. There's no dipole moment, and the molecule is non-polar. But in case of cis, the net dipole moment is not equal to 0, and hence it is polar. Okay, so cis is greater than trans, the dipole moment. Okay, now let's take another example where I have methane, hydrogen, double bond, CH3, H. Here you can see both the methane are in the same direction. So this is the cis form. Okay, take another example where methane is in the opposite direction. So that means it is the trans form. Okay. Now let's draw the dipoles. Dipole always, whenever there is carbon and carbon that has double bonds, usually the doubly bonded carbon will be more electronegative. Okay. So we draw the dipole from methane to carbon, from methane to carbon. Okay. So suppose this is mu dash and suppose this is mu dash. Okay. Now, for hydrogen, it is from hydrogen to carbon. It is from hydrogen to carbon. And in the cis form, you can see they are not cancelling each other. Okay, so the mu net is not equal to 0. Therefore, this molecule is polar. Okay. In case of transform, I have the dipole from methane to carbon, from methane to carbon. This is mu dash, mu dash. They are coming in the opposite direction. See, in this particular case, it is not the dipole mu and mu dash, not opposite. So that is why they don't cancel. Even mu and mu are also not coming in opposite direction. So the net dipole is 0, right? But in case of transform. Mu and mu dash are canceling each other. Similarly, if I say hydrogen, mu, this is mu. They are also, mu and mu are canceling each other. So the net dipole moment is equal to 0. Therefore, it is non-polar. Okay. In case of cis, they are adding up. It's not canceling. Okay. Mu dash and mu not getting cancelled. Okay. So that means here also the dipole moment of cis is greater than that of trans. Right. Looking at an exceptional condition, exception. I have carbon double bond, CH3, hydrogen, Cl. Okay, so here the hydrogen is in opposite direction, so this is trans. Carbon double bond, chlorine, methane. Hydrogen and hydrogen are in opposite same direction, so this is the cis form. Okay, now let's write down the dipoles. Always, whenever there's this carbon and doubly bonded carbon, the doubly bonded carbon will be more electronegative. Here, chlorine is more electronegative. So I draw the dipole from carbon to chlorine. Okay, then I have hydrogen. Hydrogen is less electronegative. So I draw like this. So this is mu, this is mu. So mu and mu cancel each other. Mu and mu cancel each other. Right? But mu dash and mu dash, they don't cancel each other. Mu dash, they don't cancel. So there is a net dipole and it is not equal to 0. Hence the molecule is non-polar, even if it is transy. Okay. In case of cis, I draw the dipole. Chlorine is more electronegative. Okay. Hydrogen to carbon, CH3 to carbon, hydrogen to carbon. So this is mu and mu. Mu and mu don't cancel each other. Here, this is mu dash and mu dash. Here the dipoles are adding up. Dipoles are adding up. So the net dipole is not equal to 0. So this molecule is also non-polar. Okay. Let's do a question. I'm giving you 4 compounds. Okay. And you need to tell which is more polar. Okay. So this is A. This is B. Chlorine. This is chlorobenzene. So dichlorocyclohexane. Third one, don't worry about the names and all. You will be learning about these soon in organic chemistry. Okay, so I'm not doing a lot of questions on organic chemistry because you have not learned much about the organic chemistry. Okay, so we'll do few questions and then we will go to the calculations. Okay, chlorine, this is chlorine. Okay, this is all dichlorobenzene. Okay, and D is, the position of chlorine is different. Okay, this is also dichlorobenzene, but the position of chlorine is different. So you need to tell me which is more polar. Okay, or now in the first case, I have, this is all carbon, right? So I have the dipole from carbon to chlorine. Yes. So this molecule is polar, right? In this case, carbon to chlorine, both cancel each other. So the net dipole is 0. So this is non-polar. They're canceling each other, right? Third one, the dipole is from carbon to chlorine, dipole is from carbon to chlorine. So the net dipole moment is 0. So this is non-polar. And in the next one, the dipole is from carbon to chlorine, here also from carbon to chlorine. Okay, and you can see the bond angle is 120 degree between the two chlorine and chlorine. So mu, there is some value of mu. So here, they are not, if you see the structure, they are not canceling each other, right? The two chlorine, they are at an angle of 120 degree. So the value of mu, there will be some resultant or net dipole moment. So this is polar. Okay. In this, if I ask you which of them is non-polar, which of them is non-polar? So I'm getting two answers, C and B. But if it is asked as an multiple choice question, you cannot give two answers, right? You have to give me one answer. So in that case, let's check B, if we have done any mistake in B. Okay. In B, this is not benzene. This is dichlorocyclohexane. They do not lie in the same plane. But in case of benzene, it is planar. The two chlorine are in the same plane. Okay. So for benzene, this answer is correct. But for cyclohexane, this answer is not correct because cyclohexane is not in the same plane. The two chlorine are in opposite direction. Okay, so the two chlorine are not opposite because this compound is not planar. The two chlorine, they don't lie in the same plane. Don't lie in the same plane. So if they are not in the same plane, do they cancel each other? They don't cancel each other. So that's why this molecule is polar. Okay, so the only non-polar molecule in this structure is the C answer, that is dichlorobenzene. What is the reason? Because benzene, the two chlorine atoms cancel each other because the benzene is planar. But in cyclobenzene, this is not planar. So they don't cancel each other. So they are polar. Okay. So this is one question. Now, in the next question, you have to tell me, compare the dipole moment of hydrides of fluorine, oxygen, and nitrogen. So that means HF, H2O, NH3. Okay, so here the dipole is from hydrogen to fluorine. So this is polar. There is difference in electronegativity. So this is more polar than water than ammonia. What is the reason? Difference in electronegativity. Then hydrides of group 16, oxygen, sulfur, Se, tellurium, selenium and tellurium. Okay, so water, H2S, H2Se, H2Te. Okay, so if we consider the difference in electronegativity, water is greater than H2S is greater than H2Se and greater than H2Te. Okay, now here also if we consider the charge factor, if we consider the charge factor and the distance factor, if we consider the charge factor, then water is correct. If we consider the distance factor, then we have to go for tellurium. But always we consider the charge more. So that is why this order is correct, where water is more polar than H2S, than H2S, H2Se, than H2Te. Okay. So if we consider, just once again repeating, if we consider the charge factor, then electronegativity of water is more. But if we consider the distance between the atom, remember, the dipole moment depends upon the charge and the distance, this internuclear distance. Now, this tellurium has bigger size, so the distance will be more here. But a while ago, I said when there is a fight between two factors, charge and distance, always the charge we consider. Okay, so this is the order where water is more polar than H2S, than H2Se, than H2Te. Okay, then very important example that comes for JEE, CH3F, CH3Cl, CH3Br, CH3I. Now, if we have to consider the dipole moment between them, so this is between carbon and fluorine, carbon and Cl, so carbon and bromine, and carbon and iodide. Okay, now CH bond is not very polar. Okay, so for now we ignore them. So over here, if we consider this CF, CCl, CBr, and CI, the first thing that comes in your mind is fluorine is highly electronegative. So if we consider the electronegativity difference, this should be the order. But these values of dipole moment has been taken experimentally. Okay, there's a small discrepancy over here. Okay, that CCl is greater than CF, then rest of the order is same. This is given by experiments, this order. Okay, because if we consider Cl and F, okay, so for Cl, because the size is big, the charge is less, distance is more. Internuclear distance, I'm talking about the internuclear distance between carbon and fluorine, that is more because fluorine is a bigger atom. But In case of carbon and fluorine, if we check, charge is more because it's a small atom, distance is less. Okay, so it should be. So the expected order is, this is the expected order. Expected order is this, but in reality, this is the order. You must remember this. Okay, how it has been proved? It has been proved by experiments. Okay, so this you please remember, this is one important question. Okay, so here CCl dominates over CF, the polarity, right? Now I have another question. If I consider which has more dipole moment, or which is more polar. Okay, I give two examples, NH3, NF3. So the moment you look at the molecule, you will say NF3, but kindly draw the two molecules, nitrogen, hydrogen, 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 with a lone pair of electron, nitrogen, fluorine, 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 with a lone pair of electrons. Okay, now draw the dipoles, hydrogen to nitrogen, hydrogen to nitrogen, hydrogen to nitrogen, and nitrogen to lone pair. Okay, there are four dipoles get adding up. Why? They're in the same direction. In case of fluorine is more electronegative. So this is the direction. How about this? All the dipoles are in opposite direction. So what about the net dipole? Net dipole is equal to 0. So who is more polar? NH3 is more polar than NF3. So just don't look at the formula. Just try to draw like this and check their dipoles, the direction, so that it's easy for you. Okay. So this is also very important. At the same time, you can hurry and make it wrong. So instead, draw diagram and then you have to check. Okay. Okay. Now let's move on to some calculation. What is the calculation about? Calculation of finding the percentage of ionic character in covalent compound. The opposite to this we have done in Fajan's rule. Okay. So here we will be calculating the percentage of ionic character in covalent compound. So we already studied that no compound is purely covalent or ionic. Even if it's a covalent compound, there will be some percentage of ionic character. Okay. So percentage of ionic character in covalent compound is given by observed dipole moment by theoretical dipole moment times 100. Okay, and this is the formula. In this, observed will be given. It will be given as it is calculated experimentally. Okay, and what we have to calculate is the theoretical one. Okay, now theoretical dipole moment, I'm writing the short form DM. Okay, dipole moment of suppose HCl. Okay, HCl, you know, it's a covalent compound. Okay, so chlorine will develop a slight negative charge and hydrogen will develop a slight positive charge. But we consider that hydrogen chloride is an ionic molecule and chlorine will get -1 charge and hydrogen will get +1 charge. Although it is not like that, but we are just assuming. Okay, so assuming this, we consider that hydrogen is getting +1 positive charge and chlorine is getting -1 negative. Okay, and then theoretical dipole moment. Okay, so the theoretical dipole moment is equal to Q times D. Okay, now this electron coming to the units. Okay, now this electron, if we consider the charge of the electron, it is given by 1/6 times 10 raised to -19 coulombs. It is also given in ESU. ESU means electrostatic unit, which is equal to 1 electrostatic unit is equal to 4.8 times 10 raised to -10 ESU. So 1 electron equal to 4.8 times 10 raised to 10 minus 10 raised to -10 ESU. This is the charge. Okay, so the charge what you would use is 4.8 times 10 raised to -10 ESU. Don't worry, we will be using these charges. Okay, now you just have to remember this value, 4.8 into 10 raised to -10 ESU. Now, mu is equal to Q times D. Now, Q is expressed in ESU times centimeter. Distance is in centimeters, divided by 10 raised to -18. And the answer that you get is expressed in DEBYE, which is small, which is a capital D. Okay, this is how you express mu. Okay, so the charge, whatever is given, is converted into ESU. Okay, okay, and then distance in centimeter divided by 10 raised to -18. Okay, so we will do one example, it will be clear. For example, one question. Observed mu dipole moment of HCl equal to 1.03 D. And HCl bond length is 1.275 Armstrong. Calculate the percentage of ionic character in HCl. Okay, sorry. Over here, 1 Armstrong is equal to 10 raised to -10 meters or 10 raised to -8 centimeter. Okay, 1 Armstrong. This conversion, I hope you know it. Okay, then consider HCl. Okay, so HCl. So we will treat this as an ionic compound. I have +1, -1. The more the charge, more closer it is to +1 or -1, the more is the compound is ionic. Okay, so here this is +1. Okay, so 1 times 4.8 into 10 raised to -10. Okay, so mu is equal to Q times D. Charge is 1. I'll write it directly, 4.8 times 10 raised to -10. And the distance given is what? 1.275. 1.275 Armstrong. That means I have to make it into centimeter times 10 raised to -8 centimeter. This is ESU. ESU divided by 10 raised to -18. Okay. So what am I finding? Theoretical. Theoretical. Because the experimental is given. Okay. What is the experimental value? Experimental value, I'll write in red. The formula is percentage of ionic character is equal to mu observed by mu theoretical times 100. Mu observed is given in the question. How much it is? Just check. 1.03 by times 100 by mu theoretical we are finding. Okay. By what formula? Q times D. In this Q is what we have to use ESU. So 4.8 times 10 raised to -10. Okay, the charge is 1. So 1 times 4.8 times 10 raised to -10 ESU times distance is given in Armstrong. I have to make it into centimeters. So I multiplied by 10 raised to -8 by 10 raised to -18. This was the formula that was given. Sorry. This was the formula that was given over here. 10 raised to -18. Okay, now here the value that comes is 4.8 into 1.275. So after cancelling the these gets cancelled. Okay. D by. Okay. Now we have to, let's consider this as equation. Let's consider this as equation 1. We have to put this value in equation 1. So I have percentage equal to 1.03 divided by 4.8 into 1.275 divided times 100, which is equal to 17%. So this is how you calculate. Only you have to remember this value of ESU. Okay. If they ask you in coulombs, you can use 1.6 times 10 raised to -19 coulomb. Okay. Okay, students, that's all for today. Have a great day.